it's going to collide into Earth because they both had velocity going into this direction, but their horizontal velocities or the diagonal velocities that may make it go past the planet are going to cancel each other out, which means everything will go white and you won't even get to finish the video. Hello everybody and welcome back to Universe Sandbox 2, and we don't really have an objective today other than science and doing one thing at random and seeing where that goes. That is the beauty of science, because you really don't know where science is really going to end up. What do we want to do? Do we want to blow up Earth? Do we want to save Earth? Do we want to turn Earth into something else? Could we change Earth's color? Can we make it so Earth can't support life? Well, we can make, that's pretty easy. What's the, let's see if we can make Earth support more life. Like, can Earth become more habitable? What if we ponder that question? So Earth's similarity in life likelihood is 99.5, but what if we reach that to a full 100? What's the deal with this 99.9? I mean, we're staring at Earth right now. That's the benchmark right there. Is it because of global warming? Like, between the time that I placed this down and 99.8. So we're becoming less Earth-like as time goes on. Let's speed up the simulation and then maybe it'll reach 99.7. So the planet is actually dying because we don't have a sun. The climate is 4.5 degrees Celsius. So what I am doing by just letting this Earth sit here, I'm actually committing genocide. Am I allowed to put this on YouTube? The systematic destruction, maybe not systematic destruction, but the very deliberate destruction of an entire civilization, an entire species, an entire planet. All life on Earth has now frozen over. Polar bears might still be alive, maybe penguins. Maybe this is when penguins finally take over the planet. This is the result of global warming, extreme global warming, to the point where most of the planet is now underwater because we lost, actually, no, we still have ice caps. We just have way more water than we actually need. What if I turn down the silicate? Actually, what if I turn up the silicate? Nope, nope, come on. Can I have the best of both worlds here, please? Okay, well, now we just turned this into a gas giant. Okay, this is the planet we have to work with now. We now just have a rock with clouds. I can shoot you with a water gun in this game. Rate 200%, spread 45 degree. So I can actually squirt the planet with the water gun, and I gave it just a smidge of water. That's actually a lot of water. That is a lot of water. Okay, all right, we're transforming our planet. Okay, fire. That should really lighten up the planet. And that's probably going to boil all the water away, or maybe not. We're actually not going to lose our water composition. And if anything, it might have added more water composition. So where was that impact? Was this the impact right here? It looks kind of circular. Or is it on this side? I don't know. Let's just speed things along here so I can... Let's just keep this spinning. So that way I can actually see where this might be. Oh, we have some snow now. We have our own ice caps. Okay. We've done a lot to Earth. We've crashed an entire Pluto into Earth, and we've managed to make it so that there's still a 70% chance of life. And we're 96% like Earth, so that's good. What is our total mass in terms of Earths? 1. We are exactly 1.00 Earths. I don't know how that's possible, considering we launched a whole Pluto into here. What happens if we launch a second Pluto? We're still 1 Earth. How long does... Oh, there we go. Wow, Pluto must be really small in terms of mass for it to finally tick up to 1.01. It took 3 Plutos. Pluto is 0.003333 repeated Earths. We're firing Sedna into this, by the way. Let's keep firing Sedna. I hope Sedna doesn't have a lot of water composition because I want to see some land get added to this thing. Just kind of carpet bomb it and heat up the place a little bit. I want to see what this ends up looking like. All right, let that spin around, and now we've turned this into a fireball. And this will take a while for it to cool down. Hopefully it doesn't end up getting white hot. It'll take a little bit and you'll cool down. So every second, 20 years is going by. Every second in real time. And then you watch the temperature. It takes that long for it to finally cool down. It's taking like over a millennium here for this to happen. Actually, this planet is black now. Maybe we can get below boiling and then magical stuff will start happening. All right, now we just have to lower that water composition. Now we're officially below boiling, which means I can probably slow this down some more. 60 degrees Celsius. We're like the temperature of an average GPU. That's fine. All right, you've managed to survive. The planet goes on. Now, after that cataclysmic event, Earth is now at 85.7% similarity, and there is a 77.7% chance of life. What if I whiz a very, very tiny star? That is actually a really interesting experiment. Okay, cosmic events. Maybe we have to introduce a little bit of stardust, but I want to get a very tiny star going so fast. But I want it to be moving so fast the Earth won't crash into this thing. Radius is 11.5 kilometers, this crab pulsar, but it's the mass of 1.4 suns. So I don't want auto launch velocity. I want to custom velocity, 10 kilometers per second. No. 1,000 kilometers per second. Or actually 100,000 kilometers per second, because this thing it needs to be like in a blink. We're gonna fire this thing. All right, there's the crab pulsar. It's gonna be that close to Earth, and remember, this tiny thing is the mass of. You can tell by the brightness of this thing, like how much energy it has. It's able to illuminate the planet. This tiny dot right here. That's what's really cool about pulsars. Pulsars are neutron stars. I don't know if they're considered the same thing, but I could be wrong. Feel free to correct me. I know neutron stars I think are also known to be really small. But pulsars, these spin really fast and they're really tiny. And I'm gonna slowly speed this up. Remember, this thing is going at 100,000 kilometers per second. And think of it in terms of Earth's diameter. Earth's diameter is probably what? 18,000, 20,000 kilometers. I could be completely wrong about that. That's just my guess, if I had to guess what Earth's radius is. What's gonna happen? Is the Earth getting closer to this thing? I can't tell. Do not suck up Earth. So far, I'm not noticing anything happening. It might be going too fast, but that's okay. Even if we're not seeing anything, I want to see if that changes the similarity of Earth evolved. So we've reached the closest point. I notice no change. It got that close. Did your temperature change? Are you now like 1,000 degrees? You're at 308 degrees Celsius. I think we were at 60 degrees before we started this? Earth reached almost 1,000 degrees Celsius in that short amount of time. Actually, it actually did tug Earth. You can see it crossing the path. It's actually pulling apart Earth. This is not an impact right here. This is what's known as Earth fell within what's known as the Roche limit. The gravitational pull between Earth and the star is so strong, it'll actually rip apart the planet. So if we speed things along here, Earth is probably going to go flying this way. That actually heated up the planet. Wow. And we're still at 902 Celsius. So it didn't tear apart the planet. It did rip a little bit of rocks out. So for a split second, there was probably a ridiculous earthquake. It probably made a huge volcano. Think a wave. Like imagine a wave of water just going up. Like there's some force is just bringing up a big tidal wave. Imagine that happening, but with land. That's like the Roche limit. It's just picking the land up. It's crumbling, obviously, because land isn't liquid, but it's a similar effect. It's probably creating all of these this tectonic activity. There's probably a massive volcano that got created. That is my best hypothesis for someone with minimal geology knowledge. Now, let's see the Earth similarity. Oh, 26.1. All right, life likelihood 0%. But that's fine because we're at 900 degrees Celsius, so that makes sense that there's going to be no life whatsoever. So we're just going to have to let another 10,000 years pass after this extinction event for the Earth to cool and eventually go back down to its normal self. I wonder if it actually vaporized all the water because it got that close. All right, so that's what we're dealing with. We have a big crater. We have an ice ball. Oh my god, it's the mass of 1.14 Earths, because that's all those sednas. Distance is 1.14 light years. Oh my god. But it's still not melting. Please melt. There we go. Okay, water has melted. The water has come back. Earth has survived. What's the composition? 94.7. Life likelihood 82.5. Earth can take a beating. You let enough time go by, the water bears will come back and repopulate everything. Anyways, what happens if we do this with two? So I want to fire one right there. I want to fire a pulsar right here. And you know what? Let's not stop there. Let's stay very close. Let's fire a pulsar right here. And let's fire a pulsar right here. So we have four pulsars within this in the relatively same area, just shining a light on Earth. Remember, this is Earth. We've just been experimenting with Earth once. Many ways where Earth can just completely get destroyed, or many ways Earth can survive extinction events. We basically are just creating extinction events that are completely impossible, but you never know. I don't know. Maybe the aliens are much more intelligent than we think, and they can do all of this same stuff. Or maybe we're just living in a simulation, and you know, we just have a really nice player right now. Pretend like it's me in control of this entire universe. I'm just feeling nice right now, and I haven't done anything really messed up yet. But at any moment, I can place 4 of these down and really mess up the planet. So play nice. Slow down. Oh God, this one's going in this direction. I think they're going to be going fast enough where they're not really going to interact. But we'll see. These two are getting pretty close, so things could get dicey, and then we'll experience a supernova. But then that'll be funny because we'll get to see what happens when Earth experiences a supernova. Don't you just love science? Okay, look at these guys just all go in different directions because I fired them all. And I wonder if they affected each other's orbits. Did those actually intersect? Those paths actually intersected, and I think they did affect each other's orbits. That does not look 100% straight right there. All right. Earth hasn't completely vaporized yet. Earth hasn't been completely sucked up into the pulsars yet. Oh, God, everyone's just looking up. All the, I don't know, a lot of time has gone by. Maybe something has evolved by now. Maybe the little fishies, the fish, the sea bears, they're intelligent sea bears. They're looking up and they're wondering what the hell is going on. Are we seeing the water actually? No. What we're seeing right now is a change in lighting. Look at that. That's pretty cool. That lighting right there, because the pulsar lighting is so focused, it's actually shifting around the planet. We're seeing, it's like you have 4 different daytimes on the planet. Earth obviously has not been destroyed yet, but I'm curious which way it's going to be tugged in. And with the whole roach limit thing I talked about earlier, I wonder if we're going to see 4 different points of Earth where it's just going to start ripping apart. We're going to see 4 hot spots where the pulsar came so close. And I'm pretty sure Earth is getting tugged this way. So I guess this one got closest, and that was ultimately the strongest force. So we're probably going to see, yep, that's exactly what we're going to see. We're going to see a point right here where Earth is going to get ripped apart. Are we going to see a point anywhere else where Earth is going to get ripped apart? Or was this like the one concentrated area where it's definitely going to happen? Well, wow. I guess it only had the effect on one side. It could be programming limitations of the game, but let's take a look at that temperature. 3,000 degrees Celsius. So that makes sense. It got to about 900 something the last time. Multiply that by 4 and then you'll end up with that. What if I did 10,000? Or what if I did 50,000 kilometers per second? And I'm going to make it launch even closer. Earth may even crash into this thing because it gets so close, because gravitational pulls become exponential. Oh, we've already melted the ice caps just by existing for the split second. You can see the water boiling. Okay. Will it be able to pass by? That got razor thin close. Okay. That's the volcano I was talking about. You can see the inception of it right there. The magnitude of the earthquakes happening right now. The mass of 1.4 times the sun. I don't even think you can fathom that. Passing Earth so close. Imagine something the sun. They're like, it's more massive than the sun, and it's emitting more energy from the sun. But it's in low Earth orbit. Think the International Space Station close. And all of that is being concentrated on one spot, that gravitational pull. The earthquakes you would get from that. It's like a bunch of nuclear bombs just went off, and it actually seems like it's like it just got grazed by a bullet. Shockwaves across the planet. You might as well have gotten hit with a massive meteor. Composition, climate. It got to 4,500 degrees Celsius with one, because we got that close. So that is a planet-ending event. Yeah, it pretty much engulfs the entire planet just from heating up on the other side. But half the planet just became a fireball, and then you know, by proximity, the rest of the planet ended up heating up as well. All right, look at all the years. Look at how many years it's taken. Oh, okay. So it takes around like 2,000 years for it to get back to normal temperature, but I went way too fast. So we're now 6,000 years in the future. Earth is now at absolute zero. So there we go. No meteor impact, but you see the burn marks on this planet. I want to fire something so fast to Earth that Earth will just completely shatter. But I want to fire something really tiny at Earth. That thing is actually a pretty good bullet. Okay, let's just speed this up and just let it crash once. So this thing is going to go at 50,000 kilometers per second. This will go relatively fast. And just take a massive chunk out of Earth because it went so fast. Just keep firing it. I'm going to spin Earth like a basketball and make my own pulsar. How fast is this thing going? Oh my God, what just happened? Did I make this thing spin so fast that... Let's see here. What's the rotational velocity of this thing? The tangential speed is 3.5 light speed. What's going on here? So if you think there aren't enough hours in a day, don't live on this planet. Should I make something orbit this thing? Oh my God. Oh my God. We're going at 1 millisecond per second and Earth is still moving this quickly. What is this experiment? I didn't know you can make speeds like that in this game. I figured like light speed, well, that's the cap. But apparently not. Can I even make this orbit? Orbit. How do you make this? Can you make the moon orbit? It's impossible. Okay, moon. So the moon is currently in free fall right now, but it doesn't appear to be moving, but it's moving. Earth is just moving that fast. And let's keep speeding up time. Nope. Still not noticing any movement from the moon. It's moving, but we're only going at 137 milliseconds per second. Let's speed things up a little more. Okay. We're at about real time. Or 1,000, is it 1,000? Yeah, 1 second per second. That's real time right there. How fast the Earth is currently moving. How? What if we fired something at this so fast we just stopped the velocity? Or actually, no, we're firing the moon like at its like rotational axis. It's okay, so now we're gonna speed things up so much. What on earth? No, Earth is moving so fast. What? Am I crazy, or did I just see a tiny Earth? The moon got really big. I'm not gonna question what I just saw. We're doing weird experiments. We're gonna go like that. We're gonna go like that. Oh my God. Oh my God. I think we're on a collision course with the planet. What just happened? Oh no, they're gonna be orbiting each other. Actually, which means it's gonna collide into Earth because they both had velocity going into this direction, but their horizontal velocities or the diagonal velocities that may make it go past the planet are gonna cancel each other out, which means everything will go white and you won't even get to finish the video. And a supernova would explode right in front of Earth. How will Earth fare? Let's look at... Oh, that's really unfortunate. It's 42,000 degrees Celsius. Well, you know what? We haven't seen anything boiling yet. We just had a point blank supernova right in front of Earth. You can already see the water boiling away from the planet. The vapors that are just gassing away from Earth. Oh, it's shrinking in size. Shrinking. And it will fizzle down into nothing. What if we do the converse experiment? What if we create a supernova and then we fire Earth through it really fast? Do you think Earth could survive? Oh, well, I just created a supernova. Well, that's perfect. So we're going in the milliseconds. We're just going to let that go. We're going to fire planet Earth super quick. It's like, I don't know, the supernova where we're flying through space right now. We think we're our solar system still. It's not. It's orbiting the Milky Way, and the Milky Way is orbiting something. Maybe this is an event that would happen when the Andromeda Galaxy and the Milky Way collide. And then stars that could be supernovaing happen to interact with one another. And our solar system is passing through a supernova from the Andromeda Galaxy. Not that this is probably not likely to happen now. Well, let's just say it did. You know, the odds. We beat the odds. We managed to pass through a supernova. Let's try 100,000 kilometers per second. You know, this is like it just happening. The supernova just happened. Earth is right here. That's not promising that we've already lost our water. Like I said, it just happened. It just happened. I didn't realize it was that tiny. This is a baby supernova. Speed it up. Why are you going that way, buddy? Is it because it's still current mid-explosion? So it just pelted you away? What? Okay, Earth, go, buddy, go. It just got punted away. It was like, no, you're not entering this thing at all. We'll even go a little bit faster. We'll go at 1,000,000 kilometers per second. So you're going at way faster than the speed of light. So this isn't even plausible anymore. Okay, so you're going to take this on directly. You're going to try and pierce the supernova. Will you make it through the other side? Can you make the trip, buddy? And the answer is... Oh my God. This thing was going at 1,000,000 kilometers per second and it managed to make a U-turn. How powerful is this thing? You know what? It's a tiny bit of mass, and this is the mass of an entire star. And we just tried to go down the center of it. But it seems like that's the answer, even though it didn't look graceful. Earth, if it was going at 1,000,000 kilometers per second, it would make it through the other side of the supernova and appear to live, but its velocity would not, because physics. You know, there's a huge hunk of mass, because remember, this is still mass. This is not just light. This is all star matter. That takes a lot of energy. When an entire planet's going at 1,000,000 kilometers per second, it actually slowed it down before Earth was able to leave its gravitational influence. Add one more zero, 10,000,000 kilometers per second, and the supernova is just getting bigger. You going, buddy? Oh, it's making the trip. It's ready and it's willing, and the supernova is so much bigger, but it hasn't lost any mass yet. But will it be able to maintain its velocity? Let's look at its motion. Speed is at 3.68 light speed. I think this one is actually going to make it. If it's going at 3.68 light speed. Yes, that answers the question. Going fast enough, and Earth can actually escape a supernova. Or actually just go right through it, just pass directly through the center. And you know what? I think we can end off this way. We're gonna see how that changes Earth's similarity. Earth's similarity is actually going up, so I bet you once this cools down, what's the climate like? Oh! Really? 257 degrees Celsius. So actually, it wasn't that toasty in there for some reason. I'm sure there was a lot of radiation, but it wasn't that toasty. Earth's similarity, I think, is just going to go back up. 61.2%. No chance of life, but that's okay. It'll go back up. Earth always finds a way. Life finds a way. All right. Yeah, I hope you guys enjoyed this video of dumb experiments, and I will see you all later. They're never influencing each other, like skewing up their orbits, and then they're all converging around the same spot. Or actually, there seems like there's multiple spots. Like there's a level right here, a level right here, a level right here, and a level right here. We need to go to the size of 3 suns. I want it to stay in equilibrium. I'm really surprised by that. Okay, we're now...